Everything you have ever thought, felt, or built exists as a pattern of matter. Your memories are electrochemical configurations in neurons made of atoms. Every monument, every city, every record of civilization is a particular arrangement of protons and electrons held in place by force. Information, at its most fundamental level, is structure, and structure requires matter to exist. But physics suggests that matter itself has an expiration date. The proton, the particle at the heart of every atom in your body, in this planet, in every star you have ever seen, may not be permanent. Grand unified theories, the most ambitious frameworks in modern physics, predict that protons eventually decay, just spontaneously, quietly, inevitably. One proton dissolving into a positron and a neutral pion, then nothing. If they are right, then the universe is not just cooling down, it is forgetting. Every atom that ever existed will one day dissolve into radiation, and the universe will lose the ability to remember anything at all. To understand proton decay, you first have to understand what a proton actually is. A proton is not a fundamental particle. It is made of 3 quarks, 2 up quarks and 1 down quark, bound together by the strong nuclear force. The strong force is the most powerful force in nature, operating at distances smaller than an atomic nucleus, holding quarks together with extraordinary intensity. In ordinary physics, protons do not decay. The standard model of particle physics predicts the proton is essentially stable, with a theoretical lifetime far exceeding the age of the universe. But the standard model is known to be incomplete. It does not explain gravity, dark matter, or why the universe contains more matter than antimatter. Grand unified theories, or GUTS, are attempts to fix these gaps by merging 3 of the 4 fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single unified framework. The first viable GUT was proposed in 1974 by Howard Georgi and Sheldon Glashow at Harvard. Their model, called SU5, was mathematically elegant and made a striking prediction. Protons decay with a half-life of approximately 10 to the 30 years. The Georgi-Glashow model predicted a specific decay mode, a proton transforming into a positron and a neutral pion. In 1982, the IMB detector, the Irvine, Michigan Brookhaven experiment, was built in a salt mine near Cleveland, Ohio, filled with 8,000 tons of ultra-pure water, and lowered deep underground to shield it from cosmic rays. The logic was simple. If protons decay, even rarely, a tank containing that many protons should register events. It found nothing. By 1986, the null result ruled out the original Georgi-Glashow SU5 model entirely. The most elegant first attempt at unification was falsified. But physicists did not abandon the search. They revised the models. Supersymmetric GUTS, theories incorporating a symmetry between matter particles and force particles, pushed the predicted proton lifetime up to around 10 to the 34 years, well beyond what IMB could detect. A new, far larger experiment was needed. In 1996, the Super-Kamiokande detector began operations in the Mozumi mine under Mount Ikeno in Gifu Prefecture, Japan. Super-K is a cylindrical stainless steel tank holding 50,000 tons of ultra-pure water, lined with 11,146 photomultiplier tubes, each 50 centimeters in diameter. It sits 1,000 meters underground, shielded by rock from surface cosmic radiation. The water inside Super-K is so chemically pure, it would pull minerals from your body if you drank it. When a charged particle moves through the water faster than light travels through water, it produces a faint cone of blue light called Cherenkov radiation. Super-K watches for those blue flashes, the fingerprints of particle interactions within its enormous volume. A proton decay event would produce a very specific ring of Cherenkov light, matching the positron-pion decay signature. Super-Kamiokande has been running for nearly 3 decades. It has detected neutrinos from supernovae, measured neutrino oscillations, and confirmed that neutrinos have mass, work that earned the Nobel Prize in Physics in 2015. But it has never detected a single proton decay event. Not one. This absence has pushed the experimental lower bound on the proton lifetime above 1.6 times 10 to the 34 years for the primary decay mode. Every year Super-K runs without seeing a decay, the lower bound tightens, squeezing the allowed parameter space of each theoretical model. In 2020, Super-K was upgraded with a gadolinium sulfate solution added to the water, improving sensitivity to neutron capture events. The upgraded detector is now called Super-K GD. Hyper-Kamiokande, currently under construction and expected to begin operations around 2027, will hold 260,000 tons of water, 5 times the volume of Super-K. If proton decay exists at rates predicted by current supersymmetric GUTS, Hyper-K should detect it within its first decade of operation. The mechanism behind proton decay in gut models involves a class of hypothetical particles called X and Y bosons. In the SU5 framework, X bosons mediate interactions between quarks and leptons, particle classes that do not normally interact directly. An X boson can briefly convert a quark into a lepton, transforming the internal composition of a proton into an unstable configuration that immediately collapses. The X bosons themselves are extraordinarily massive, on the order of 10 to the 15 GeV, which is why the interactions they mediate are so vanishingly rare. But quantum mechanics allows this, and over vast timescales, the probability accumulates. Proton decay, if it occurs, is not a catastrophe. It is an accountant's correction, the universe balancing a ledger deferred since the first microsecond of existence. Now consider what proton decay means for information. Every piece of information in the physical universe is encoded as structure. Claude Shannon formalized this in 1948, showing that information is a measure of the reduction of uncertainty, the specific arrangement of a system distinguishing it from all other possible arrangements. A book contains information because its specific sequence of ink marks is one of an astronomically large number of possible sequences. DNA contains information because its specific sequence of base pairs encodes instructions that no other sequence would encode. Your memories contain information because the precise synaptic weights in your neural network represent your particular history, a configuration that has never existed before and will never exist again. All of this information requires physical structure, and physical structure requires atoms, and atoms require protons. Rolf Landauer at IBM established in 1961 that information erasure is a physical process. Erasing one bit of information generates a minimum of kT ln the 2 joules of heat, where K is Boltzmann's constant and T is temperature. This is Landauer's principle, and it connects thermodynamics directly to information theory. It means that when a proton decays, the information it was encoding is permanently released as entropy, erased. The second law of thermodynamics states that entropy in a closed system always increases. Stars are engines that locally reverse entropy, fusing hydrogen into heavier elements, creating complex structures, but they do so by radiating enormous entropy into the void. Every ordered structure in the universe is a temporary eddy in a river flowing toward disorder. Thermodynamic heat death, the state in which the universe reaches maximum entropy, was first discussed by Ludwig Boltzmann and William Thomson in the 1850s. In this picture, the universe cools, all free energy gradients disappear, and nothing can happen anymore. But heat death is usually described as a temperature problem, a universe too cold and too uniform for any process to occur. Proton decay reframes heat death as an information problem. It is not merely that the universe becomes too cold to think. It is that the universe loses the physical substrate on which thought, on which any distinction, any structure, any meaning can be written. Freeman Dyson, in his 1979 paper Time Without End, argued that life and intelligence could theoretically persist indefinitely in a cooling universe by slowing their metabolism to match declining temperatures. His argument assumed that matter itself would persist. Proton decay eliminates that assumption. If protons decay, Dyson's scenario collapses, not from the cold, but from the dissolution of the very particles any structure must be built from. By around 10 to the 40 years, assuming the most optimistic proton lifetime estimates, essentially all protons in the universe will have decayed. At that point, atoms no longer exist. Planets, stars, and stellar remnants dissolve into dilute clouds of electrons, positrons, and photons. There is no surface on which to write. There is no substrate on which any pattern can be maintained. The universe becomes informationally sterile. It is not just that everything is forgotten. It is that the universe loses the capacity to remember. Consider the Voyager 1 spacecraft, launched in 1977, carrying a gold-plated copper record inscribed with sounds and images from Earth. It is now more than 23 billion kilometers from Earth, in interstellar space. Gold is chemically inert and physically robust, one of the most durable materials humanity has ever worked with. In the absence of collisions, a gold record in interstellar space could survive for billions of years. But every gold atom in that record is made of protons, 79 protons per gold nucleus, precisely arranged. Within 10 to the 40 years, every one of those protons dissolves. The grooves etched into the record, the encoded greetings, the music, the images of humanity, cease to exist as physical distinctions. The record becomes radiation, and the information it carried, the only physical artifact humanity has ever sent beyond the solar system, is permanently erased. This is Landauer's erasure principle applied cosmologically. Not just the loss of specific information, but the loss of the capacity to hold information at all. The universe's information storage capacity drops to zero. What remains after proton decay is a diffuse, homogeneous gas of fundamental particles, electrons, positrons, neutrinos, photons, at temperatures indistinguishable from each other. No gradients, no structure, no distinction. This is the dark era, a universe that has reached near-perfect symmetry through the patient, silent dissolution of every particle that ever held a meaningful relationship to any other particle. It is worth noting that proton decay has not been detected. It remains a prediction, not an established fact. If protons are stable, if every gut is wrong in this specific way, then matter persists longer, transmuting slowly to iron over 10 to the 1500 years through pycnonuclear fusion. But even in that scenario, the information capacity of the universe still collapses. Iron spheres in thermal equilibrium with the cosmic background can encode almost no information. The erasure happens either way, faster with proton decay, slower without it. Now bring this back to you. Right now, the neurons in your brain are firing in patterns that have never occurred before in the history of the universe. The specific configuration of synaptic weights encoding your memory of your first day of school, or the face of someone you love, or the sensation of a particular afternoon, that configuration has never existed and will never exist again. When you die, that configuration is lost. The atoms scatter, the pattern dissolves. But the atoms remain. They go on to form other things. The carbon in your body was forged in a star that died before the sun was born, and after you, it will become part of something else entirely. The matter persists even when the pattern is gone. Proton decay removes even that consolation. Eventually, far beyond any timescale that maps onto human intuition, even the atoms scatter. The carbon, the iron, the gold, all of it dissolves into radiation. There is no substrate left to form anything from. But here is what makes this strange, rather than simply bleak. The proton that will one day decay was forged in the first second of the universe, survived 13.8 billion years of cosmic history, and spent a fraction of that time inside a human brain, thinking about its own eventual dissolution. It will spend the vast remainder of its existence drifting through cold space before finally, after an incomprehensible wait, quietly vanishing. The thought you are having right now is one of the most complex events in the history of that proton. Most of its existence is cold silence. This, right now, is the extraordinary part. The universe does not care about information. It does not try to preserve patterns. It moves, without intention, toward the state of minimum distinction. And yet, here, briefly, distinction exists. Complex, fragile, improbable distinction. A proton that has spent most of eternity as part of nothing memorable has spent a cosmic instant as part of a mind. That is not a small thing. The universe forgets everything. But first, it remembered you.